Hello everyone. My name is Nikita, and I'm a DevOps engineer at TeamCity Cloud initiative. And today I would like to speak about some of the lessons we learned so far running cloud beta in AWS. A bit of history first. TeamCity is a cloud-based offering, has some history. It's not the first time team tries to come up with the TeamCity Cloud. So back in 2017, there were plans to provide a multi-tenant installation, which resulted in a test drive project hosted at teamcity.jetbrains.com. But for different reasons, it has been discontinued. So test drive ran for quite a while, and some of the architectural decisions behind TeamCity JetBrains.com, which is currently active and still supported, some of the open source projects are built there, then were reused in the beginning of the TeamCity Cloud in its current implementation. So Cloud Initiative got relaunched in September 2019. And by the end of the year, we had a working prototype. And this time we picked a bit different approach, with each client receiving a standalone TeamCity instance, which we manage from the lifecycle perspective. And we host databases, we host agents. And we launched a private invite-based beta this February, and it went well until we rolled out beta publicly in July, and we are still in a public beta phase. This slide depicts the trend. We have new signups each day, with average for around 15 instances per day in October, 4 weeks in October. So we get some very valuable feedback. And so far, the public beta taught us a couple of very useful lessons, which we are willing to share because they might help hosting an on-premise installation in AWS. So this is the primary purpose of this talk. Let's start with a high-level overview of TeamCity architecture. So every server is basically a Tomcat hosting a TeamCity process. All of this is wrapped in a JVM, hosted in a JVM-compatible environment, which could be an OpenJDK Docker image or Corretto image, for example. So clients, users, and build agents, they are communicating with the server via URLs, via HTTP and both HTTPS, which are supported. And it is not necessary for server to have route to agents, so communication can be unidirectional. It utilizes locally mounted storage for logs, for project data, for plugins, for caches. All of this could be an NFS mount. Of course, performance should be taken into consideration because storing caches on network storage, network attached storage is not always a good idea. So also a critical part of the whole application is this database, which TeamCity uses in JDBC driver to communicate with a external SQL database, which can be MySQL, Microsoft SQL Server, or PostgreSQL. So although they do provide the ability to use HSQL as a storage, it's not production-ready solution, so it's not here. And finally, the critical part is the artifact storage, which can be a local amount, but it can be a cloud-based storage as well, for example, S3. This is set per project, so basically one TeamCity server can have both local storage and both cloud-based storage. As mentioned previously, TeamCity Cloud already had a concept and a base architecture, so TeamCity JetBrains was a predecessor to this. So in the beginning, we already knew what we should focus on. So we already had a vision of what services in Amazon we can start to use. So this is an Elastic Block Store to provide volumes to virtual machines, Elastic File System to provide storage between different containers, for example, and S3 for artifact storage. We use MySQL hosted as a relational database service instance. And for application hosting, currently we use Elastic Container Service, which is in turn based on EC2 machines powered by autoscaling groups, and it's paired with application load balancer currently. And We also use different Amazon services like Route 53 for DNS hosting, both public namespaces and private namespaces for service discovery, for example, and Systems Manager for parameter storage or to provide us ourselves with the remote access to virtual machines. So this is how TeamCity Cloud looks in Amazon in general. So every TeamCity instance is a separate ECS managed Docker container. It is available only via the HTTPS through application load balancer, and outbound internet access is provided through NAT instances for both servers and both cloud-hosted agents. We create a separate schema per client, and each client has an isolated user. So actually, each client is limited to a single schema for, of course, for isolation, for security purposes. Same actually applies to any shared resource we use. For example, if we're talking about shared artifact storage, each client is isolated based on identity access management policies. So this is the principle we apply to every kind of shared service we use in TeamCity Cloud. An important thing to mention is that we actually manage TeamCity Cloud using TeamCity and a couple of management services, management APIs, we call them. They are actually responsible for storing the metadata about environment, like number of clients, or sharding data, like how much more space we have in databases, or load balancer to make decision to scale or not. So I won't dive much into details of how managers are designed because it's still a work in progress and it's kind of out of scope of the current topic. But behind them, we have an actual execution environment where we actually execute our infrastructure as code, automation, which is currently Terraform, and a couple of more API calls. And actually, a whole automation runs through URL hooks. So when a client asks for a new TeamCity server via the forum, we actually create a couple of API calls, and we create deployments via the TeamCity server. So this is how it looks. So we have a separate TeamCity instance which performs the jobs, which in turn create the instances, assign instances to clients, and this instance can also upgrade itself on the fly. So after all, it's still a TeamCity Cloud client. It's just a separate instance, although it's, of course, isolated. And also, there is no mistake on the slide. We're currently running our processes to migrate to Elastic Kubernetes service. I will talk a bit more about this later, but as of now, we think that it scales better for our needs. Moving on to the actual lessons we learned. So primarily networking, VPCs and subnets. Initially, the network design was pretty straightforward. So all resources use it, NAT gateway or internet gateway, if applicable, if it's public subnet, for outbound access with a default route configured. As simple as that. So this approach, of course, had negative effects when it started to scale. Utilizing NAT gateway has become, for us, unpredictable in terms of costs for both outbound and inbound network utilization. And especially since by default, we can't predict the amount of data or location where we download or upload this because we run client code within the agent network. We understood that we should move on from the NAT gateway. Apart from that, of course, default routing did not consider our default network flows like agent to S3 upload or download from Elastic Container Registry to Elastic Container Service. When we start TeamCity server on a new machine, of course, we have to download quite a big image. And obviously, in the beginning, we also ran into subnet calculation errors because if we want to extend our functionality with things like service discovery, private namespaces, they require more network interfaces within the VPC, and this requires more addresses. So VPC size should be estimated from the beginning. So possible solutions to these problems were NAT instance, which is a separate EC2 machine, virtual machine configured via autoscaling group. It's based on the official image, and it works pretty well. As for a default routing, we moved on to VPC endpoints, which are actually locally available routes for any AWS service we use. There's quite a lot of services available, but for us, it was very important to not use NAT instance while accessing Elastic Container Registry and S3. And of course, we just carefully repicked subnets, added additional CIDR blocks, and in the end, we just redesigned our whole VPC when we migrated to Elastic Kubernetes service. And moving on to application load balancing, being ECS clients, we relied heavily on out-of-the-box integration, which has actually a service definition, which contains link to target group, which is linked to a listener, which is a part of the load balancer. So in this case, Elastic Container Service runs a lot of requests to Elastic Load Balancing to just check on the target health. When the cluster is scaled, we are currently running like a 1,500 services. So at this scale, it creates a lot of requests, and we easily ran into throttling exceptions, and we still are running into them from time to time. We just need to ask for a service limit request from the Amazon support team. And also, since every ECS service in this case requires a separate rule, so DNS entry, host header, which points to a dynamically generated target group name, we have to create a lot of different rules on application load balancers. And there is a hard limit. We can't create more than 100 client-specified rules. So load balancers should be sharded when we're running ECS with application load balancing integration. Regarding storage, in general, everything that went wrong was related to incorrect prediction for burstable workloads. So some parts of stateful data were stored in Elastic file system for containers. And although in general application does not require fast disk in these areas, in situation when a lot of applications perform their disk-related activities on the start, for example, simultaneously, EFS throughput gets exhausted quickly. So you should carefully calculate what you need, because you may need to create a provisioned to set performance tier to provisioned performance, or one should control burstable workloads in different way. So the monitoring should be set up accordingly, because we still need to track exact number of client connections and, of course, a throughput utilization. We can set up a warning that we're running low on the throughput, and we need to decide to scale or not. So apart from that, in the beginning of the project, there was also no nice features like EFS access points, which are available now, and according ECS integration as well. So we had to perform EFS mounting on the start of the container instance machine. And this requires setting up alerts for EFS client connections carefully, because obviously this number should be equal to number of servers that are mounting EFS. Otherwise, we can run into data issues. And apart from that, S3-wise, we need to create a reusable policy. Well, at least try to create a reusable policy to manage S3 access. More on that a bit later. More about Elastic Container Services is that we actually use AWS log driver along with Log4j to send logs from the TeamCity to offload them and visualize them then. But this worked well until eventually, for some reason, logs.amazon AWS.com stopped responding in time, which resulted in TeamCity kind of getting locked because that log collection fails. So it's necessary to consider that logging can lock out the application. There is a solution to that. It's one of the solutions to just set the AWS logs to non-blocking mode, which can result in losing some of the log entries, but at least it won't lock out the application. And more about Elastic Container Service. ECR mentioned Elastic Container Registry issue mentioned earlier was a result of simultaneous cold start of a lot of machines. So every machine downloaded quite a big image. And if there is an NAT instance of small size, and instance types in Amazon, there are different with network throughput, of course, CPU and memory, and this may result into quick exhaustion of the network throughput. So this also may be solved with the creation of VPC endpoint for Elastic Container Registry URLs, but API URLs and metadata URLs, and actually download URLs. Besides that, S3 access is also should be configured internally to avoid these issues. And so moving on, TeamCity also may open a lot of files in some cases. So ulimits should also be configured accordingly. It does not apply only to ECS. It just applies to any TeamCity server running in a container. And yes, as I've already said, we recommend using local endpoints if the workload of your TeamCity server requires uploading a lot of data to S3. About roles, about identity access management, we would advise to consider hard limits on policy attachments and from number of roles, because these are hard limits. And we think that application that does not, in fact, need to have access to S3 on execution phase, again, if we are talking about running this in a container, for example, in ECS, but it does need access to Elastic Container Registry, for example. So it's a nice idea to differentiate this in Elastic Container Service on execution role and task role. So far, we've also created an IAM role per client, which is good from security perspective, systems manager access, S3, VPC access. But at scale, this may result into running in a hard limit of 5,000 roles per AWS account. So although for us currently this is not a big issue, we have some more room, we think that it's generally a good idea to implement attribute-based access, which can help a lot. And identity access management service can now actually provide dynamically set variables in each request, which is cool because based on this, we can create a generalized role, which can be easily reused. And you don't need to create a client-specific role anymore. Just out of the box, you have a client-specific tag, for example. which can help a lot. Unfortunately, it does not help in Elastic Container Service, where we don't have access to managing the actual API call to IAM when the container starts. But we're looking into this in Elastic Kubernetes Service environment, which is a bit different and provides a bit more control about how we assume identity access management role. Moving on to databases, obviously the main thing we can ask to consider is that backup job always can go wrong. And this might affect connectivity non-obviously. For example, during one of the nightly backup jobs, according to AWS support, our RDS instance had unpredictable I/O burst, which led to suspension. And then backup job had to be rerun. So we saw not this picture in our logs, we just saw a couple of more events where RDS stated that we need to restore the database, backup did not finish, we redid a backup, it went well, everything was fine, and even from TeamCity perspective, there was no access interruption. But behind the curtains, application created a lot of piled the connections, and then eventually connection pool or thread pool actually got exhausted and applications just stopped. So this should be taken into consideration as well. Generally, of course, it's a good idea to create backups from read replicas, or even better, from multi-AZ, according to Amazon, if this is acceptable and applicable. And of course, database instances and connections must be fine-tuned. For example, database properties for TeamCity Server should have adequate timeout setup. And from the database service, instance size can be selected differently based on max connections, for example. So moving on to general recommendations, apart from common container-specific issues we had for actually running a stateful applications, so we need to share data, share volumes. Well, we think that TeamCity performs quite well hosted within the container, so it's a general recommendation to actually run TeamCity Server in container, because TeamCity JetBrains also runs as an ECS control Docker image, which is cool. Auto-scaling group can help a lot with standard management procedures, and lifecycle hooks can create a valuable link between Elastic Container Service and auto-scaling group in terms of infrastructure refresh. So when we need to drain instances, we can automatically update the auto-scaling group. Of course, there are also things like capacity providers, which also help with infrastructure refresh. Also, I've already mentioned, but mention once again, that API limits can be visualized and monitored, at least their error rate. And CloudTrail can help here a lot. And we also think that in general, for quite a lot of issues or problems we had, for them, AWS probably already had a solution. So for example, Systems Manager does a good job providing remote access currently for us via Session Manager. We don't have to use best-in hosts and painfully rotate SSH keys. We just log in using our IAM fine-grained policies, and we have remote access. It's also probably a good idea to use Cognito instead of firewalls, because it integrates well with application load balancer, so you can rather easily restrict access using your identity provider, for example, without having to manage IP addresses anymore. It's not always applicable, but probably it's a good thing to consider. And for example, we don't need to use self-host an SMTP server if we can use SES, Simple Email Service. And more than that, simple managed service plugin for TeamCity does even more. It can ban bounced emails. So generally, it's a good idea to just use this to send your emails from server. And to conclude with the general recommendations and my presentation, overall, I would like to mention that TeamCity already has a lot to offer out of the box for cloud integration. For example, we would like to highlight it once more because surprisingly, there is a lot of clients seemingly unaware of this. For example, the on-demand start of the EC2-based agents, spot instances also are supported, or build features to log into Docker registry, which can perform Docker login automatically, Docker login, Docker pull, Docker push, Docker tag, etc. And that also you can use as free as an artifact storage out of the box, which is rather cool, in my opinion. So I think that is it. I hope it was helpful. So we probably can move on to Q&A.
Yeah. Thanks, Nikita. That was really helpful. And I want to reiterate one of the things Nikita mentioned. We do have a pretty wide array of out-of-the-box functionality with cloud instances, whether you're using AWS, Azure, Google Cloud today. If you are running your build agents in cloud environments, you can offload the ability for TeamCity to spin up and spin down those agents. In Amazon, it's based off of an AMI or just a direct EC2 instance you create. And it really gives you a lot more flexibility as far as your license utilization, making sure that the licenses that you're paying for are being utilized as much as possible. So if you haven't looked at any of those capabilities, you don't need to move to TeamCity Cloud to utilize those capabilities. You can take advantage of them today. We do have some questions in the chat. Nikita, I'll start off with one of the more technical ones. In your architecture, you guys are using ECS as opposed to EKS. Is there a reason for that?
It is. I'm sorry, I should have mentioned this more in the presentation. Yes, we're currently moving away from ECS to Kubernetes. And the primary decision behind this was that we don't scale well with out-of-the-box load balancer integration. We have to manage load balancer, and yes, Amazon has just released the application load balancer controller, which also can be used with EKS currently only. And apart from that, we ran into a lot of throttling issues running quite a big ECS cluster we have, and we think that EKS provides a bit more freedom in terms of managing load balancers. For example, we use self-managed ingress instead of using application load balancer now. So yeah, I think this was the primary reason for us moving to EKS.
Okay, great. One more question for you, and this is more about the capabilities. And I'll add, we will be releasing more information about, I guess, the individual capabilities within TeamCity Cloud. But one of the questions is, does TeamCity Cloud provide the same features as the on-premise traditional server version that most of the folks on the call are probably using? Is it the same UI? Do we expect any differences? Could you talk a little bit about some of the differences or some of the similarities between TeamCity and what will be available in TeamCity Cloud?
Sure. Actually, the main principle was when we started TeamCity Cloud in 2019, the main principle was just to take the base on-premise product and just enhance this functionality. So basically, we built TeamCity Cloud on top of the regular TeamCity. We use the same code, we use the same UI. So far, there are no actual plans to have a different UI for TeamCity Cloud. Of course, from the client perspective, like we will provide a cabinet to track usage of TeamCity Cloud. But in general, there is a a parity between on-premise TeamCity and TeamCity Cloud. We don't want to differentiate them a lot.
Okay, great. Yeah, and I mentioned this in the chat. As far as like functional differences, a lot of the administration capabilities in TeamCity Cloud are obviously going to be hidden since we're hosting all of that infrastructure. Some things like being able to install third-party plugins are also really only available on a case-by-case basis. But by and large, we're trying to provide the same experience. TeamCity Cloud, you will be able to use JetBrains provided agents, or you can bring your own self-hosted agents to that environment.
I also wanted to double down on one of the points from Nikita's last slide. It doesn't relate directly to TeamCity Cloud, but I think it's quite relevant in the current circumstances. So Nikita mentioned there is a built-in feature in TeamCity that allows you to add a Docker registry connection to your builds in your project. And what that basically means is that TeamCity will automatically sign into a Docker registry on your behalf when it does any of the Docker-related builds. And given the newest Docker limitations on the number of available pools, as you might know, this is a very helpful feature, and we definitely urge you to please do that for your builds, especially if you're using one of the free Docker accounts. At least you will be not anonymous, so you'll get more pools out of for your Docker builds.
All right. Appreciate it, Nikita. We'll let you off the hook here.